So, hello everyone. Welcome to IEEE Big Data Analytics tutorial series. This is Qiu Shi. Today, we are honored to have Professor David Harvey from the University of Oxford. His talk is about data-driven battery health diagnosis in real-world applications. As we know, accurate diagnostics and prognostic of battery health improves overall system performance in electric cars and renewable energy systems. In this talk, two key questions will be answered. First, how to handle modeling challenges, including parameter variability and non-linearities. Second, how to develop validated predictions of future health. This talk will discuss recent approaches to tackle some of these exciting topics. As Professor Harvey pointed out, this talk will be around 1 hour. At the end of this talk, there will be a Q&A. During the talk, please feel free to ask us questions, or you can unmute yourself to ask your questions. And now I'll give the speaker to Professor Wang. He will have a brief introduction of Professor Harvey.
It's my great pleasure to have David here. He is a professor of engineering science at the University of Oxford, UK. He leads a group researching modeling and control of energy storage systems, and he has a particular focus on lithium batteries for electrical vehicles. And you will hear about grid and off-grid storage analysis. He received his master's degree from Electrical and Information Science of University of Cambridge in 2002, and his PhD from Imperial College London in 2010. Since 2010, in the past 12 years, he has co-authored more than 80 plus peer-reviewed journals and conference and 5 patents. He's editor for IEEE Transactions on Industrial Informatics, and also the OUP journal, Oxford Open Energy. He's co-founder of Oxford Battery Modeling Symposium, and he's also the co-founder of Brio Power, a company that is growing out of his lab in 2016. Finally, he is a recipient of fundings from EPSRC, Innovate UK, UKRI, Faraday Institution, Continental AG, and Siemens. As you can see, he had a lot of funding that is commercialized from his lab technologies. Finally, thank you, David. I appreciate your time. Please feel free to start your exciting talk.
Okay, great. Thanks for the introduction. Can everyone hear me okay?
Yes.
Yeah, okay. Just before I get into detail, I have 2 screens here. Because of the way PowerPoint works, I might not be able to see you guys. So if you want to interrupt me, just start talking, that's fine. Or say, excuse me or something, just because I can't kind of see all of your pictures. But it's great to meet you. And thanks for the very kind introductions and the invitation to give this talk. As I said earlier, I think I might pause a few times for questions through the presentation instead of waiting until the very end. So we'll see how we go. Before I get into detail, also, I should say that a lot of this work that I'm going to talk about today was, of course, done by one of my research group, a very good PhD student called Antti Autio, who recently finished his PhD. He's gone to work in industry. But I should give full credit to him for doing all of the heavy lifting on this amazing project. So this picture here, we were talking about it earlier. This shows a battery system made by one of our collaborators, a company called Bbox. They build solar battery off-grid systems, which are mainly used in sub-Saharan Africa, but also in other parts of the world, across Central Asia and other countries, remote rural areas. And the key result that I want to talk about in this presentation is a technique that we've developed to extract battery state of health from live data from these systems, so just measurements of current, voltage, and temperature, and then use that to identify batteries which are failing. I suppose that's the kind of sophisticated version of the story. The less sophisticated version is I'm going to tell you how to estimate the internal resistance of a battery. And I guess I'm speaking to electrical engineers, so you probably know how to do that already. But actually, it turns out to be surprisingly complicated because, of course, the internal resistance depends on temperature, depends on state of charge, and so on. So another thing I'll say is most of the methods I talk about here, although I'm actually going to give data from lead acid batteries, which is kind of old technology, they will work on lithium ion as well. The reason why I talk about lead acid is because we had a lot of data from lead acid systems. We are currently getting data from another company on lithium ion, but we just haven't published that yet. So the method is kind of agnostic to the battery chemistry. And you'll see why that is. It's because basically we use equivalent circuit models. So again, IEEE electrical engineers, we love equivalent circuit models. So here we're talking about equivalent circuit models of batteries. And really what I'm going to talk about is how do we parameterize equivalent circuit models, which again, it sounds like a simple problem, turns out to be quite subtle and quite interesting. Okay, let's get started. So this presentation is roughly divided into two sections. First of all, I'll spend some time motivating the problem, and I'll give you a general introduction and explain why we care about doing this and why it's a difficult challenge. I'll talk about some existing methods as well. And then I'll talk about the approach that we've developed, which joins up a machine learning technique called Gaussian process regression with equivalent circuit model parameterization. I'll talk about how we apply that to state of health diagnosis in solar connected batteries. And then I'll extend that to talk about other types of battery models and other types of applications. And by the way, I think you mentioned in the introduction that I was going to talk about grid connected batteries. We do work on grid connected batteries in my team, but I'm not actually going to talk about that today. But if anyone is interested in that, I'm very happy to give you a few minutes about that at the end. These techniques, of course, they don't really care about the application. So the method I'm talking about now, you could apply it to electric vehicles, you could apply it to grid connected batteries if you want, if you have the data available, of course. Okay, so let's consider the challenge of learning about battery health from real world data. You can all appreciate that batteries fail. Okay, I want you to picture the scene that you get in your car and you press the button or turn the key and the engine tries to start and then it doesn't start. Okay, and actually this happened to me a few years ago, about 3 years ago, and I remember taking a picture at the time and saying, well, that's embarrassing, battery researcher's car battery dies. And of course in this case it was a classic scene, and it was quite easy to fix because we got someone to come and replace the battery, and the battery is just a small part of the car in this case. But actually, this was 3 years ago. We've now got rid of this car and we have an electric car, and of course the battery is a much bigger deal in the electric car. If the electric car battery is going to fail, I really want to know about that, right? That's a game changer. And the same argument goes for big grid connected battery systems. This could be tens of millions of dollars investment, or fleets of electric buses. Again, huge investment, lots of capital, or the off-grid systems I'm going to talk about today. People are depending on these for their phone charging, for their radio comms, and if the battery fails, it can be difficult to replace because it's in a remote area. So battery failure prediction is important. But unfortunately, batteries are a lot like people. They're quite fragile. They want to be at a comfortable temperature. This picture kind of shows some thoughts about this. I mean, for lithium-ion batteries, if we go to very high temperatures, we have issues with safety. We could, in the extreme case, we could have a thermal runaway event, which is very bad. If it's just slightly elevated temperature, we might have accelerated aging. If we go to very low temperatures, then we can have safety issues as well if we charge our batteries at low temperatures. So ideally for lithium ion, we want to be kind of at 30 degrees C, or maybe a bit lower, 20 degrees C, maybe this is a bit high. So that's one issue. Another thing is actually the imbalance of temperature from cell to cell. So if we have a big pack in an EV or something, we want to make sure that all of the battery cells in that EV are behaving at a similar temperature. We don't want a big temperature difference. So temperature is one issue. Mechanical fragility is another issue. This picture shows some modules from a Tesla Model S car, and you probably know this already, but inside that we have a lot of these cylindrical lithium-ion cells called 18650s, and you can see that they're all inside a metal case, right, to keep it mechanically robust, and that is then packaged inside lots of other packaging here. And so if this is punctured, you know, we could have a safety issue, so we want to make sure that the battery is mechanically safe. And then finally, we also see that batteries gradually degrade over time, and eventually they would die. And these graphs here basically just show some simulations of the capacity fade in a battery, which is, I'm sure we all know about that with our mobile phones, but you know, if my phone it is quite old, if it's 3 or 4 years old, I maybe have to charge it every day instead of every 2 days. So that's like the size of the fuel tank is decreasing. And that's what we mean when we talk about capacity fade. And this graph just shows some measurements of capacity fade from real batteries. And in this presentation, I'm mainly going to be focusing on this third thing, okay? So we could talk about temperature, we could talk about mechanical stuff. They're interesting topics, but we're just going to talk about lifetime in this presentation. And why do we want to try and estimate battery state of health, battery lifetime from real world data instead of from lab tests? Let's try and motivate that a bit further. There are lots of benefits for doing this, but ultimately I think it's about improving the cost effectiveness of battery systems. So first of all, you get some immediate benefits for safety. For example, we might have early warning of a failure. We might be able to shut everything down before it kind of gets serious. We might be able to do some preventative maintenance, remove a battery from a large pack which needs to be replaced, and so on. Secondly, we are always interested in optimizing the development and manufacturing production of these systems. And literature has shown, you might be aware if you've done any work in this space, of a paper a few years ago which looked at using some interesting optimization techniques to try and speed up the process of coming up with new charging protocols for batteries. So we're always interested in trying to get answers more quickly. We don't want to wait 2 years to do tests on batteries. We want to try and accelerate the understanding we get by using data in a clever way. And the more data we have, the more we can do that. Thirdly, we want to make sure that the warranties and insurance policies for large batteries are correctly priced, right? Not too expensive. This graph shows some capacity fade data from University of Munich based on a Volkswagen ID.3 electric car. And what this graph is showing, there's quite a lot of data on here. I won't explain it all in detail, but what this is really saying is that the performance of the real car has basically been very good compared to like lab tests of batteries. So essentially, I think just relying on lab tests might make you think quite pessimistic things about electric vehicle performance in the real world. So the real world stuff is in the colored data on this graph, and the lab stuff is in black and white. And that's because a lot of lab tests are kind of accelerated, higher temperatures, more cycles per day than the real world, and so on. So we need real world data because we don't want to be overly pessimistic about the performance of batteries either. And then finally, another reason for being good at estimating lifetime from field data is because second life applications are becoming increasingly important as we struggle to keep up with the demand for new batteries. We know that battery production involves lots of raw material extraction and processing. And I think there was a prediction a couple of years ago in The Economist that the demand for lithium would actually outstrip the supply by about 2027 at the current rate. So the more we can reliably diagnose how well performing a system at the end of first life is, like I take my electric car, I think I've had it for 10 years, maybe it's time to turn it into something else. Instead of just throwing it away, what we want to do is make sure that the maximum value is taken from that battery pack. So maybe that battery pack gets put into a grid energy storage system instead. But to do that, we need to make sure that we can reliably diagnose the performance of the batteries after 10 years. And so we need, again, to use as much data as possible to get a good picture of that. Okay. So estimating state of health from field data as well as lab data is important, but it's also quite challenging. And this slide shows about 18 months of voltage measurements from a lead acid battery, basically the one in the first slide, in the title slide, the same kind of product. And you can see that it's a bit messy. There's some stuff here which we maybe, there's a gap. There's things we can't necessarily explain. The system was turned off, the voltage just drops for a month or whatever. If we zoom in and look at a certain day, we can see that there's no controlled cycling. So we have charging from solar, so we can see that there's kind of a messy charging pattern here. The temperature is fluctuating all over the place, the state of charge is fluctuating all over the place. And what this means is that, yes, we have a lot of data, but validating our predictions is really difficult because we can't go in and intervene and take the system offline and do like control tests. So we have to estimate things, but without having any direct measurements to compare to. So if I can give you a picture, it's a little bit like looking for a needle in a haystack, but without really knowing what the needle looks like. So we only have like a blurry picture of what the needle itself looks like. So it's a difficult problem. And another issue relating to this is that in the lab, we usually have a lot of metadata when we're testing batteries. For example, you can see in this table here all kinds of information that we can go and measure, and we can populate with information relating to where the materials came from and so on and so forth. But even basic things in the field can be really difficult to get hold of. So we are unlikely to have so-called half cell voltage measurements, which you might have in a lab. So we can say no to that. And we are very unlikely to have the kinds of measurements shown in this table, which are really kind of materials level measurements of things that we would need if we want to do a very detailed simulation of a battery. So we could say no to that. And as a result of this, if we're going to do any diagnosis on batteries using field data, we need to stick to models and methods that are very simple and don't have lots of parameters, lots of physical parameters, and lots of complexity that we don't have data to support, basically. We also need methods that are flexible and can deal with noise and uncertainty. And this uncertainty issue is very, very important, which is shown in this next slide. Basically, we have to make sure that we handle uncertainty in a principled way. Because when we do estimation in the real world, which is kind of illustrated on the right-hand side of this figure, what this figure is really saying, let me try and explain this. So what this figure is really saying is we have capacity measurements over time versus cycle number. In the lab, each of those capacity measurements has a certain uncertainty associated with it. Effectively, we're measuring a parameter, and it's like a probability distribution, which has some variance. But that's quite tight, right? We're quite precise in our measurements, or our estimates, I should say, of this parameter. And what that means is if we then extrapolate into the future what the behavior of the battery capacity is going to be, battery health in the future, we can do that in a relatively certain way. Whereas in the real world, first of all, we have a lot more uncertainty with these capacity estimates because we can't just directly measure the capacity. We have to infer it from model fits. And because of that greater variance on those capacity estimates, when we then extrapolate that into the future, we have a lot more uncertainty on the battery health in the future as well. Plus, of course, we don't know that the usage pattern is going to be exactly the same in the future. So there's uncertainty caused by intrinsic kind of identifiability issues, I guess we could say, plus uncertainty of what the user is actually going to do. So it's a difficult problem, this life prediction problem. Okay, I will take a little pause there just to see, does anyone have any questions at this stage before we get into further detail? No? Okay, that's fine. Okay, so now I'm going to talk for a few minutes about some of the existing methods for diagnosing battery health. And basically, to do indirect estimation, as I'm sure many of you appreciate, we tend to this idea of using model-based approaches or observers, very common from the control engineering world. And this diagram shows what I'm talking about in the context of batteries. So we can see we have effectively got the real battery here in pink. We have current, as we assume current is like the input and voltage is the output and temperature is the output. Of course, we can run these models with voltage as the input and current as the output, but it's generally easiest to run them with current as the input. And then we have our battery management system, which is a piece of electronic hardware and software that sits on the car or the off-grid system or whatever. And inside the brain of that, we have a battery model which is running. And that could be anything from a very simple circuit model, like I'm going to talk about, to a much more complicated electrochemical model. But let's just say it's a model for now. And what we do is we measure the current, we feed that into the battery model, and then we measure the voltage, say, and we compare the voltage that the model is predicting to the measured voltage, and we have an error which we feed back through maybe some kind of gain matrix or whatever into the model as an additional input. And in this way, as I'm sure you're familiar, we use negative feedback to drive the battery model states to converge, hopefully, to the states of the real world. And that means that if we're using the right kind of model and we're doing this correctly, then we can use things like we can use states in the model to basically infer things that we can't directly measure, like state of charge and state of health. Okay, hopefully that idea is quite familiar to electrical engineers. Just to give a bit more detail, a very typical kind of model that we see used in battery management systems is a circuit model, which looks a bit like this. And this would often actually be used to represent the dynamics of the whole battery pack. So this is not for an individual cell, this is for a whole pack, or maybe a submodule or something like that. So I guess this is a sort of a empirical circuit model which tries to explain the behavior of the voltage and current in the battery. And what we've got inside this model is a series resistance, RS over here, an RC pair, which explains some of the kind of dynamics of the voltage response, and then a voltage source, which is a nonlinear function of the battery state of charge, okay? And the battery state of charge is related to the integral of the current. So if we write down a state space system to represent this, it's going to look something like this. So we have two states. The first state, U1, is just the voltage across this RC pair, and the second state, U2, is the state of charge. And because the state of charge is just related to the integral of the current, we have zeros in this matrix here for the second row. And then we have an output equation as well, which tells us how the terminal voltage that we measure here relates to the states. So we've got this nonlinear function of OCV that I mentioned, and then the voltage U1, and then finally the voltage from the resistor RS. So that's a pretty simple state space model. We've got a linear dynamic system and a nonlinear output equation, but the nonlinearity is quite well behaved because it's just a static nonlinearity in the output. The U2 thing is the state of charge. The Q is the capacity of the battery, which you can think of as a scaling function on this this thing here. So as the battery capacity fades, we can imagine that the relationship between V0 and SSC is staying the same. But if we express this in units of amp hours, then it would be squeezing, so we have less amp hours. And then finally, we have this resistance here. And what I want to draw your attention to is that the three things I've written here, SSC, capacity, and resistance, are three things we're interested in. So SSC is something we want to estimate to know what the state of charge is. How much range do I have in my electric car? We need to know the SOC for that. But the health-related parameters are related to the capacity and resistance. And whether we care more about capacity or resistance will depend on the application. So if it's a energy application, like an electric car, we'll care about capacity. But some battery applications, we care a lot about resistance because we care about power, okay? For example, I heard that electric trains, for example, which have batteries for getting over short sections of the line where there's no electric power supply, they tend to care about power, so they care about resistance because the whole system is thermally limited, the battery is being used at high power. So in that case, we would tend to use RS as our health metric rather than Q. Okay. So how do we use these models to diagnose battery health? Well, the classic thing, which has been in the literature for a long time, at least 15 years, is to essentially run two observers, one which gives you the SOC, assuming that Q and RS are quasi-static, and then a sort of slower observer, which gradually adapts the parameters Q and RS over a much longer time period, generally with a random walk, which is what's shown here. That should say RK plus 1. Sorry, that should not be an equal sign. So what that says is that the parameter value at a given time step is the same as it was before, plus some noise. Okay, this is not always a very reliable approach. It's not always guaranteed to go in the right place. It's a joint state parameter estimation problem. And by assuming that the parameters are following a random walk, we're actually throwing lots of information away about how the value at time k is correlated with the value at time k minus 1. We're assuming they're not connected and actually, or they're only connected through noise. But actually, of course, we would expect the capacity fade in a battery to be, relatively smooth over time if I go back to this picture. So we'd expect quite a strong correlation between the capacity measurement today and the capacity measurement last week, for example. How can we improve on this and try and do a better job and get smoother and more reliable estimates? Okay, and so this is really a question of how can we define some kind of improved approach for updating the parameters instead of using a random walk? How can we define what the parameter dynamics actually look like? So I'm going to show you some of the methods that people have used in the literature. So one approach is very empirical, but is essentially to say, I'm going to go and do lots of measurements in the lab on how batteries fade over time, and then fit some curves to those measurements. And that's what's shown in these graphs here. We can see that capacity loss as a function of temperature, for example, and time follows these kind of exponential curves. Similarly, as a function of state of charge and time, similar kind of exponential curves. And we can parameterize these with correlations and functions and sort of empirical equations, if you like. So that's one approach, but it's very much get some data, fit it with some curves, and hope for the best. And it doesn't necessarily give you a rule for how you update that with live information. Another approach which we see in the literature is to do kind of much more of a black box thing. And so here we won't use a battery model at all. We won't use a circuit model, but we will just map directly from some measurements to some labeled output data. So for example, we've done some work where we map directly from changes in the voltage over a few time points to capacity estimates. Or we could look at correlations between battery capacity for one cell, which is cell number 3 here, and other cells which have aged further, such as cell number 1 and 2 here. And there's lots and lots of papers here. I mean, it's really an area that's exploded in the last 2 or 3 years. You can almost pick a machine learning method, I don't know, neural networks or Gaussian processes or whatever, pick a data set and there'll be a paper about that. So whatever combination of machine learning tools and data sets you can think of, someone's written a paper on it. And we've done some work as well, which is referenced here in these 2 papers here, going back a few years now, using data from Aachen University, I think, in this case. Oh no, sorry, this is NASA. This is NASA data. We've got some ongoing work with Aachen University, which is this right-hand side slide here. And this was a couple of years ago, but this shows, again, a completely black box approach where we use neural network and we just map directly from the entire trajectory of capacity fade to the future kind of trajectory. So to summarize, we could go kind of model-based using kind of circuit models or whatever and look at the parameters and evolve those parameters over time. That's one approach. Or we could go for a different approach, which is much more black box and just say we have lots of data and we just want to learn how the battery capacity fades over time from the data. I think a big issue with these approaches, these black box kind of data-driven approaches, is that they're dependent on the data. We don't necessarily know how well this will extrapolate beyond the data set that it's already seen. It's a classic kind of machine learning problem. Because of that, it's very useful to try and have models which kind of meet in the middle and are some combination, in my view, of data-driven, but also maybe a circuit model or something that you can have some interpretability of. So that brings me to the next part of the talk, which is how do we combine the best of both worlds and try and have a combination of circuit models in this case, and the flexibility that we get from machine learning tools. Before we get into that, does anyone have any questions at this stage? If you do, just unmute and speak or raise a hand or whatever. Nope. Okay. Okay, so we want to try and make the best of both worlds, physically motivated models and machine learning tools. And the question is, can that help us both understand what's going on, but also get good performance? So I wanted to show you first, before we get into detail on that, some battery data. So this is from the system that I mentioned earlier. And the kind of data that is being measured is quite simple, but we have voltage, current, which has been normalized to C rate by dividing by the capacity, and then temperature at the bottom here. And you can see, this data goes for 1, 2, 3 years. If we zoom in, we can see some typical features of these systems. They basically are used diurnally, so they get charged, for example, during the day from solar, then discharged a little bit in the evening, and then maybe overnight is the main discharge. Maybe there's a light gets left on, or some radios and TVs are used, and then a light gets left on. And then the following day, the same thing happens again. Charge it up, sit for a little bit, and then discharge. And we can also see that there's a temperature fluctuation, which is quite large. We're sort of 15 degrees C. Actually, sorry, forgive me. Temperature fluctuation over the year is quite large. Actually, temperature fluctuation in this case is quite small between day and night. But there's some temperature fluctuation. And we can also see that most of the currents are actually quite small. In this particular application, it's a very low current application. So the kinds of loads that people are using with these systems would be things like phones, lights, TVs, radios, and so on. Now, with this particular system, it's lead acid, and for reasons I won't go into, it's actually very difficult to measure the capacity of lead acid batteries. So it's easier to measure the resistance. And so we stuck to using the resistance as our health metric. And so the question is, how do we take this data and estimate the resistance from it? Okay. And our initial approach was actually to use what I showed you a few slides ago and basically do that kind of random walk, dual Kalman filter type thing. But actually, when we did that, it didn't work very well. Okay, so we took an initial discharge cycle. We actually didn't use all the data. We just took the discharge cycles, and then we tried to fit a very simple Thevenin circuit model like this with a voltage source and resistor. And what we found was that our estimates looked very, very noisy. So we had resistances which were like extremely noisy, and even if we put a smoothing filter through this, we still get something that isn't very useful. And the question is, why is this? Okay, is this a problem with the model-based observer? Is it a physical reason? Is it a sensor issue? What is the problem? And after lots of investigation, we actually found that the main reason for this fluctuation, it's quite interesting, was not related to a sensor issue, was not related to an observability issue. It was a physical thing, and it was because the battery itself, the resistance is a very strong function of temperature, state of charge, and current. Okay, so it's not, the resistance is not constant. It's physically impacted by what temperature, current, and so on it's at. So it's like a nonlinear resistor, I guess. And to illustrate this, this is just a simulation, but you can see here on the left, basically a two-dimensional function. So the z-axis is the resistance, and then the t is like time, and the x is like state of charge. And what this is really showing is that because the battery state of charge strongly impacts the resistance, if we just measure the resistance and don't account for the state of charge, we get a signal that looks very noisy, which is this blue signal on the right. So actually what we need to do is try to fit this entire surface in 2D, and then we can do something like take a slice through it, and then we get a nice smooth estimate of the resistance at a calibrated condition like state of charge is 0.5. And there are good physical reasons why the resistance of a battery varies with current and state of charge and so on. it's because of things like the exchange current density is concentration dependent and so on. So if we don't account for this operational dependence, then we will think our estimate is very noisy. So it's very important that we do account for this. Okay. Let's go on to the next slide. Okay, so what we want to do is we want to try and fit a circuit model like this, but where some of these circuit parameters are not constant, they're actually functions. And what we want to do is learn those functions from data. And we can formulate this problem as essentially a supervised machine learning problem, and therefore there are lots of good tools that we can use to do this. And so the approach that we've come up with basically combines the circuit model approach with a machine learning approach to learn the resistance function. And to make it even simpler, we actually ignore this RC pair. So our model is literally still just the voltage source and the resistor in the first case. But now we have this resistor itself is now quite a complicated nonlinear function of time, temperature, state of charge, and current. And so this function f is what we're trying to learn from the data. Okay. Now, although this model looks simple, we can actually extend these ideas back to more complex models. For example, we've recently done some work, which we haven't quite published yet, but where we also do the same thing with this RC pair. So we assume that those are not constants, but we learn them as functions from data as well. I'll show you some initial results in a few slides' time. So how do we learn these functional parameters? And the method we chose to use is to use Gaussian processes. So I'm now going to take a few slides to try and briefly explain to you how Gaussian processes work. So Gaussian processes, if you've not heard of them before, they're a very interesting technique for learning functions from data. Okay. The way that I'm going to try and explain them to you is by saying, all of this is from a Bayesian framework. So I should first, before I explain what a Gaussian process is, I'll try and explain what I mean by a Bayesian framework. So in a Bayesian framework, what we are saying is that we consider parameters to be probabilistic, okay? So what that means is, for example, let's say I'm trying to estimate the value of I don't know, the slope of a function relating x and y. We could fit the values of x and y and get the slope using maximum likelihood, for example. But if we wanted that slope as a probability density, then we have to introduce something called a prior, which is basically our prior assumption of what that thing would look like as a probability density. And using Bayes' rule, we can combine the likelihood function, the prior, and get the posterior, so-called posterior, and that would be a probability distribution. So extending that idea, so if we can do this on an individual value of a parameter, we can extend this idea using Gaussian processes to actually think of estimating functions from data. So not just estimating individual values as probability densities, but estimating entire functions as probabilistic functions, okay? And what this picture is showing is a kind of an illustration of what I've just talked about. So the same idea applies, right? So if we had an individual value, we'd have a prior probability of that, and we'd have some likelihood calculated from data, and then we'd have a posterior. But we can do the same with a function. So we can have a prior of the function itself, which is what's shown on the left hand here. Then we can go and observe some data, which is what these black points in the middle of this slide, oops, sorry, show, forgive me. Hang on a sec, just trying to get my laser back. Oh, where's it gone? No, doesn't want to do it. Come on. There we go. Okay, so on the left-hand side, don't worry too much about the details of what this is, but basically the left-hand side is showing us our prior assumption of what the function would look like, which in this case, because it's a probabilistic function, it's like a sea of probability, which has a mean and a variance. Okay, then we observe some data, and the right-hand side is showing us the posterior function having observed the data. And again, it has a mean and a variance. and without going into like super large amounts of detail, the really cool thing about GPs is that actually we can think of this as fitting data using infinite basis functions. What you can think of is every time we observe data, it's like a magnet. We're sort of attracting the prior towards the data that we've got. Another way of thinking about this is that it's like doing a random walk through the observed data. Okay, that's why it's a process, a Gaussian process. So it's like we're taking a Gaussian process and we're kind of randomly walking through our observed data. And what's cool about this is we can now make predictions in between or away from the existing data points. And the brilliant thing about Gaussian processes, they're quite complicated, but the thing I want you to understand is that we can make these predictions using very simple linear algebra, which is what's shown up here in these equations, okay? So if we want to make a prediction of the mean at a new point, which I call U star, or mu star, sorry, then it's just a simple combination of the existing points and something called the kernel function, which sits in K. And the same if we want to make predictions of what's happening in the variance, it's a simple bit of linear algebra applied to the existing data points and some stuff that sits in this thing called K. What's really interesting about Gaussian processes is that unlike something like a neural network, where I have lots of parameters which I fit to data, and then I carry those parameters around and I can use that model to do predictions by just carrying those parameters around. In the Gaussian process, the data itself is the model. So if I want to make predictions, I have to use the existing data set and take these linear combinations, I have to do this linear algebra using the existing data set, which is a bit of a problem because they don't scale very well. Because if I want to make predictions using a bigger and bigger data set, I have to carry the whole data set around. So I'll talk about that in a second. But when we talk about fitting a Gaussian process to data, what we're really talking about is fitting a couple of parameters that sit inside these functions, which are called hyperparameters. So things like the variance of the noise, which is like the variance of the observations themselves, or some parameters relating to the length scale of the covariance between points. But generally speaking, there'll be relatively few hyperparameters, and most of the information is just the data itself, okay? Okay, so Gaussian processes are really interesting because they're also very flexible. So we can have lots of different types of prior functions, if you like. So we could say that we have a prior set of functions which look a bit like this, which is something called a squared exponential covariance, like radial basis functions, if you've heard of those. And that will give us behavior when we extrapolate, which kind of extrapolates to the prior variance and the prior mean, which in this case is 0. Or we could say, well, we know that we are trying to track something that is actually changing over time and is going to keep on a trajectory. And in that case, we might want to have a Gaussian process which is a so-called non-stationary Gaussian process, in which case the variance could grow over time. And if we do that, then we could track something which has a mean and a variance which kind of, don't just revert to the prior mean over time in a long range extrapolation. So we can impose some kind of loose stuff to do with smoothness and periodicity, but essentially Gaussian processes give us this very flexible way of fitting data. But there is a problem with Gaussian processes, and it's called, well, it's sort of so-called big N problem, which you can sort of see if you are familiar with the maths of these things at all. I'm sure you know about this already. But generally speaking, there are two things we want to be able to calculate with a Gaussian process. Okay, there's the mean and the variance at new points where we want to make predictions. Okay. And there are closed form solutions for these, which are shown by these equations here. And the second thing we want to do is we want to calculate something called the energy function, which is given by this equation at the bottom here. And this is essentially the log of the marginal likelihood, okay, which is the probability of the output given the input and some parameters. This thing here is the thing that we need to optimize when we're fitting the hyperparameters of the GP. the issue with these equations is that they involve inverting matrices which are n by n, where n is the number of data points that we have. So computationally, we've got this problem that Gaussian processes do not scale well. And lots of solutions have been proposed for this over the last several years. But in this particular work, we were very pleased to discover and apply actually a very neat solution to this problem, which I'll come to on the next slide. So hopefully you're still with me at this point. We'll zoom out in a second from the detail. But to get around this scaling challenge, we actually picked up some very excellent work from Finland, from Simo Saakka and Arno Solin in Aalto University in Finland. And their approach is to say, well, look, a Gaussian process can be expressed as the solution to a stochastic differential equation, okay? Which sounds very complicated. Basically what that means is that we can write, let's have a look. So we've got the Gaussian process here, shown up here. We can make predictions by knowing what this function is. We can equivalently write this function as buried inside a differential equation, okay? Which is a function of time, and x, where x is the sort of measurement dimension. So you can imagine in this particular problem, that would be things like state of charge and temperature and so on. And in this case, this thing on the right, it actually is a linear system, okay? So in this case, W is a noise input, and we have these things L and F and H, which are matrices which relate directly to the kernel functions in the Gaussian process. But what's really cool about this is we can find the solution to this linear stochastic differential equation using standard Kalman filter. And what that means is that if we have a lot of data in one dimension, so for example, in our data set, we had a lot of data in time, but not that much data in state of charge or temperature or current, we can then deal with that data recursively and fit a Gaussian process to it in a way that doesn't scale badly. So if I show you this animation, you'll maybe see what I see. So what we do is we basically run a Kalman filter through the data in the forward direction, and that gives us something called the filtering distribution, which is given by this probability here. And then we run a backwards path in the reverse direction, which you'll see is what's happening now in the animation, and that gives us the smoothing distribution. This is called a Rauchtung-Striebel smoother. And if we do this, so forwards and backwards, then we get exactly the same result as if we had fitted the GP in a batch mode, which is what the previous slides were talking about. So this is very, very cool, because what this gives you is a tool which allows you to fit the hyperparameters of the Gaussian process and compute predictions of the posterior mean and variance, but avoid having to invert huge matrices. And that means we can now use Gaussian processes to fit functions to very large data sets at least in one dimension. Okay, let's zoom back out to the battery problem. So let's put these pieces together and apply it to thinking about battery health. This is an overall pipeline of the algorithm that we developed. We've got the off-grid systems feeding data in from the left here. Again, voltage, current, and temperature is what we measure. We use Gaussian process regression to basically extract internal resistance from battery systems, but as a function of temperature, time, state of charge, and current. And when I say fit, what we're really doing is we're trying to minimize the difference between the predicted and the measured voltage. So that's how, so we feed the current into the model, and we adjust the resistance, which is this whole Gaussian process, to get the best fit with between the predicted and the measured voltage. And then, okay, at that point you could say, well, great, that seems to be interesting. It gives us a bunch of these health metrics, which I'll come on to in a second. But how do we know if it's working or not? So at that point, we actually also trained a classifier. We realized that there was independent failure data available from real systems in the field. So we could then train a classifier to basically try and predict whether a system was healthy or failing, having been independently labeled by a workshop. So I'll show you some details of that in a second. So the battery model we used, as I mentioned earlier, is very simple. It's just terminal voltage is a nonlinear function of state of charge. So this is open circuit voltage, and then this complicated kind of resistance, which is modeled with a Gaussian process. And then we have epsilon, which is just additive noise. And then the Gaussian process has zero mean and a kernel function k. And the inputs to the Gaussian process are 4-dimensional. So it's temperature, state of charge, current, and time, which is this theta variable. We can see why we need this range of inputs, because if you look at the data here, this is a histogram of all of the data that we were dealing with. You can see that we actually span quite a large range of temperatures from 18 to 42 degrees C. We also actually have non-uniform sampling as well. So I mentioned earlier that a Gaussian process is uniquely defined through its kernel functions. The kernel functions are shown here, and we actually use two different kernel functions, one of which defines the relationship between the resistance and time, which is this non-stationary one shown here. But the other one is the stationary one, which defines the relationship between resistance and temperature, current, and state of charge. And I won't go into detail, but these are the equations for those kernel functions. And really what we're trying to do is we're trying to learn the hyperparameters, which are the sort of sigma parameters in these equations. And so it's essentially the length scales and some noise parameters. Okay. So when we put this all together, what we end up is a really nice state space system, which has a kind of block diagonal structure. And that means we can actually run, if you like, the battery model and the parameter dynamics at the same time. So we have this kind of augmented state space system, which has the model I showed you way back at the beginning of the presentation, that kind of idea, and now this extra submatrix which relates to the parameter dynamics. Just to kind of, I think maybe I'll gloss over these details in the interest of time, but we had to do some stuff to discretize the dimensions of state of charge and temperature and so on. We used clustering to do that, and then we do estimates of the hyperparameter posteriors using map estimation. We do the forward pass to get the energy function, which helps us to fit the hyperparameters, and then finally we do the backward pass to actually get the posteriors for the batteries. And this is a system, just to give you some numbers, which involves roughly 1,000 batteries. We had about 40 million rows of data, and we managed to fit these Gaussian processes in about an hour and 20 minutes on an Apache Spark cluster with 30 cores. So you could not do that if you didn't do this recursive implementation of the GP that I was talking about earlier. Okay. So let me show you kind of what it looks like. So this is a picture of how that Gaussian process kind of adapts to data as you kind of see more data. So you can see the graphs in the bottom are kind of slices through this 4-dimensional function. The bottom left is resistance as a function of state of charge. The red one is resistance function of current. Then we've got temperature in green and time. And you can see what's quite cool about this is we actually see things that we would expect from physics. So we see that the resistance decreases as the current increases. And that's expected because essentially batteries have this nonlinear kind of dependence on current. The temperature has this negative temperature dependence as well, which again is what we expect based on the properties of the electrolyte in the battery. And then finally, in the gray, we get a health metric, which is like a damage metric, which is going up over time, but now it's calibrated. So we can actually compare lots of different batteries and put them all under the same conditions and make comparisons. And so we might be able to do things like, sorry, my animation's a bit slow here. We might be able to do things like threshold these estimates. I'll just go to the end. There we go. Sorry. Oh no. Apologies, my PowerPoint isn't working, but what it used to show is kind of a threshold on this gray thing saying, well, if the resistance is above a certain value, then maybe that's a problem. We should send the unit to get checked out. So the question is, what do we do next? We've got a system which takes voltage, current, temperature, gives us resistance as this function, And everything looks really promising, but how do we use this to actually predict failure? And how do we know if it's correct? And to do this, we need separate validation data. And this is a big challenge, which is not talked about very much in battery and machine learning papers, I don't think. But we were very lucky. The data set we used, the company actually, when a system breaks down, the battery gets taken in for repair, and they test it in a separate workshop. They check what the failure condition really is. They test the battery separately, and then in their database, it gets logged like the failure was because the battery failed. So we could know for our data set independently whether the battery had failed or not. And we were able to use that data to train a classifier. And what's a classifier? I'm sure you know what a classifier is, but it's basically another function that we learn which has inputs and outputs, but the output now is binary. Okay, so the output is healthy or faulty. And in this case, we had data from more than 1,000 batteries, which provided a very rich data set for training a classifier. And so one of the inputs we could use was the resistance estimates that I mentioned earlier, these trajectories. But we could also actually define other aging factors, which is what's shown here. So we could define aging factors like age, calendar age, charge throughput, number of cycles, mean voltage, mean temperature, and so on. So what we're trying to do here is go from diagnosing battery health to a lifetime model where we predict lifetime. And what we did was we took all of our data, we trained different classifiers to try and predict battery failure under different scenarios with different sets of input and different prediction lengths. And this graph here shows the performance of these classifiers. So let me explain what you're looking at. So basically 0 is the point where the battery failed. Okay, so this is the failure point. And then as I go further to the right, this is the forecast horizon. So if I go to 56, that's basically saying 8 weeks before the battery failed, can I predict that it was going to fail? Okay. And then the different colors are showing how different sets of inputs to the classifier perform in terms of overall accuracy, which we measure using something called balanced accuracy. So the best performance we get is by combining estimates of resistance and gradient of resistance, so R0 and also dR0 dt, plus a number of these aging factors at the time when the battery fails. And if we look at that data, we get above 80% accuracy in predicting is the battery going to fail or not based on just these inputs. If we use only the resistance estimates and ignore all of these other factors that we compute here, then it drops down to kind of 75%. If we use only the stress factors, then we get this red graph, so it's like 70%. And then if we use a method in the literature, which was the state of the art at the time, which is this random walk approach for parameters that I talked about earlier, we get this green line, which starts at about 65% and drops to about 50% as we push the prediction horizon out to 8 weeks. And by the way, 50% in this case is no better than flipping a coin. Right? So it's basically randomly like assigning healthy or faulty. So I think this is a really exciting result because basically what this is saying is we can blend together population factors, like a population lifetime model, with specific data from a specific battery to get a prediction which is 20% better than the benchmark. And we can make that prediction up to, in this case, 1 or 2 months before the failure occurs, which is sufficient time for a company like Bbox to be able to do preventative maintenance, given that they're operating in very remote rural locations. And a side benefit of this approach is we also get access to what the classifier thinks is important. So which of these factors is mostly influencing the behavior? And we can see actually mean temperature and mean voltage are very important for the aging of these particular batteries. Okay. I think I'll skip this particular slide in the interest of time. I wanted to just spend the last 2 minutes just talking about where this work currently is at. So we are extending it to apply to lithium-ion and beyond low current off-grid cases to things like electric cars. How do these approaches extend to more complex circuits, such as the one with the RC pair in that you can see here? This is a circuit model which would be much more appropriate for something like an electric vehicle. And what I've got here is a video which basically shows how we would parameterize this circuit model using synthetic voltage, current, and temperature data, where we assume that these RC parameters now are actually a function of state of charge and time. So this is quite a complicated parameter estimation problem, because we now have parameters that are buried inside the dynamics, which are not constants, but are functions of latent variables. And you can see, if I run this video, we start with our oops, sorry, it's a bit slow. Apologies. Okay, I'll just pause it so you can have a look at what's going on. So what you can see is, as we start to see some measurements, current, voltage, and temperature, we start to be able to fit these functional parameters. So the top one here, tau, is just the RC time constant. The bottom one here is the inverse of the capacitance in this RC pair. And then the one below that is the capacity of the battery. And then on the right-hand side, we have R0, the series resistance, which I've already talked about. But you can see that at the point where we only have data at high state of charge, we still have a lot of uncertainty at low state of charge, because we just haven't seen any data. And then as we see more data at low states of charge, we start to lock in to where we would expect to be. Apologies, the video is a bit slow over Zoom. Yeah. Anyway, okay. Hopefully you get the idea. I think my computer's having a bad day. If I go on to the next slide, I'll show you what this looks like when we start to use not just synthetic data, but some real world data. So we've applied this to aging data from Samsung cells in collaboration with Aachen University in Germany. This aging data is shown on the left, and you can see that it's quite complicated cell drive cycles, a bit like an electric car on a motorway or whatever. Battery voltage is dropping, current is going all over the place, and the temperature is doing different things. But we take this data, which takes this cycling and does it lots and lots and lots of times, and the batteries are aging over 1 or 2 years. And from that, we can actually learn with these techniques what the capacity is doing, how the capacity is fading, and what the resistance is doing, how the resistance is increasing. But also, at the bottom of this graph, we can see what these RC parameters are looking like as a function of state of charge and as a function of time. And so this is really exciting, because not only are we getting health metrics which are useful, as shown on the top, and we can extrapolate them into the future as well, but we're actually getting kind of fingerprints of the individual RC component functions, which are indicative of interesting things that are going on in these batteries. Okay, I'm going to wrap it up now. So just to summarize, I know I've said a lot of different things. I hope some of it has been interesting for you. I think the take-home messages and will come through in a second, but to summarize what I've said, so I think data and model-driven approaches to state of health, they both have strengths and weaknesses. We should take a combination of both of them to get the best approach. On the model-driven side, we have circuit models. We have things like insight, some level interpretability, maybe some reliability of extrapolation. On the pure data-driven side, we might get a lot of accuracy if we have enough data. We might get flexibility if we have enough data, but we might sacrifice interpretability and generality. So somewhere in the middle, maybe we can combine the two things. And one way of doing this I've shown you is to use semi-empirical circuit type models with Bayesian methods to learn parameters. And we can extend these concepts. So we can start looking at fleet level data. We could say, can I come up with a prior mean for a new cell parameter based on data I've already got? The Bayesian approach allows us to have a principled way of learning about parameters based on all of the information we have. Quick advert for a couple of papers on this, if you're interested in these topics. The one on the left is a perspective paper in Joule, which is basically about the general issues that I've talked about, the opportunities and the challenges of this kind of lifetime prediction, lifetime modeling. The one on the right is a detailed and specific paper about what I've talked about in this presentation, which is the prediction of battery end of life from solar off-grid system field data. And then some general comments just to finish. I think the first thing to say is that, and I can't emphasize this strongly enough, data-driven approaches are only as good as the data that we have. If we have a lot of data, we might be able to do a lot, but if we don't have a lot of data, then we're very limited. I personally think there needs to be more focus on simple but interpretable models. I think there's been an awful lot of work done, certainly in the battery machine learning world, using things which are quite uninterpretable. And you see a lot of machine learning papers which are like, I've built a model which predicts something, here's the result, but it doesn't necessarily give you any scientific insight into why that's interesting or useful, or what you're actually learning. And then the third thing, scale up is difficult, and actually we're engaged in a long discussion with the company that we had the data from here about how do we implement this, what are the financial benefits to having this kind of prediction. And I think those of us who are researching this space need to do some work to really demonstrate the benefits. I'd like to just again thank my research group, particularly Antti, who did most of the hard work. This is him here in the third position from the left, plus funding from BBOX Faraday Institution as well. And if you want to get in touch with me, my email address is at the bottom, website as well, and I'm on Twitter. Thanks very much.
Thank you, Professor Harvey, for the wonderful talk. Yeah, I really enjoy it. So I have collected some questions from the audience. So I start from the first one. So first, yes, how can I incorporate battery use behavior into the prediction of state of health? Because yeah, I guess maybe different people have different battery usage patterns or performance. How can we incorporate that? Yeah,
that's a very, very good question. And I mean, I think just to emphasize, let's have a look. Yeah, if I go back to this slide, for example, you can see here that actually these batteries are all being used in the same kind of way. And so we've kind of ignored that problem a little bit in this particular slide. And so okay, a very simple way of doing this is to assume that the use in the future is going to be the same as the use in the past. Okay, maybe that's not a good assumption, but that's one approach. And if we do that, then we can just extrapolate along the trajectory, which is what's shown, for example, here. So then the question becomes, I think there's two aspects to this question which are interesting. One is, how does the battery aging depend on the usage? And the second one is, what happens if the usage changes, right? So let's say like I'm at this point where the red line is, my past use was maybe an electric car, my future use is not going to be an electric car, it's going to be a grid storage system. So how do I like extrapolate for a different future? That's a really interesting question. To some extent, this work has covered that. If I go back to this slide here, what's really interesting about this classifier is that this graph in the bottom right corner, this aging model, actually gives me a usage-related lifetime model. What it says is that mean temperature and mean voltage have an impact on probability of failure. And so this, but I think this is a population level average usage or average lifetime model. And so I think it's a great question, and actually it's an area of active work, which is to say, how do I build up usage-related lifetime models, which are this kind of thing that I've got on here, but also not just population average, but actually specific to different batteries and specific to different usage cases, but transferable to other usage cases and so on. So I think there's still a lot of work to be done on that. And a lot of that work is going to require us to get more data relating to aging and different usage scenarios.
Yes. I think we need a generalized method to, otherwise it's analysis will be case by case, right? Different user, different user behavior. So
it's true. I think for this particular data set, we could say that this model is general, but it's probably only valid for if I just show you this, it's probably only valid for the range of voltage, current, and temperature in the data set, right? Which is what's shown here on this slide, which I didn't really talk about. So if we see data which has a similar histogram of temperature, state of charge, and current, then we could probably use the lifetime model that we've developed through this classifier.
Yes, I see. Yes, the second question so it's in page 18.
Yep, 1 second.
Oh, yes.
Let's go back. Oh, yeah.
So yeah, why is it jittering on the right-hand side figure?
Oh, yeah, that's a good question. Yeah, actually, you see this kind of behavior quite a lot in data sets of battery health. Yeah, it's a good question. I think you see it here a little bit as well, actually, on the left-hand side. So often the way that these lab battery tests are done is they will cycle some batteries, charge and discharge the batteries, then they'll wait for a few hours, then they'll do a bit more charge and discharge, then they'll wait, and so on. And sometimes you see that the capacity apparently seems to recover, right? So for example, it might be that this jump back upwards here has been caused by someone like leaving the system, pausing the system for 2 weeks for the summer holidays or something like that. And then the capacity kind of jumps back up. And so I think what this is telling us is it is real, right? It's not like measurement noise. It's real, but it's what it's telling us is that the lab measurements are not very indicative of real world because they kind of accelerate, squashing a lot more tests into a shorter time. And actually, if we let the batteries relax for a few days, often we do recover capacity. And it's because of the fact that the concentration gradients inside the batteries stabilize. So the lithium kind of goes to much more uniform concentration distribution. So I think it's related to that, if you like. I don't know if that answers your question. It's a good question.
Thank you. So the next question for the JP posterior, I think around the 20 something page.
This kind of thing, maybe?
Yes, I guess so. So
yeah,
the question is, the data pattern depends on the region. Can we use only observed 5 data points to detect phi, theta and mu on the right-hand side? For
yes,
for
yeah.
It's not finished yet. Sorry. For
keep going.
non-stationary JP, do we have varying theta and mu parameters?
Maybe it's better if I go back to this one. Okay. I mean, this is a good question, real detailed stuff. So let me, and I didn't explain it very well. Sorry. End of a long day here. It's like 6 o'clock. Okay. So let's just be clear what we're looking at. So what is a Gaussian process? So a Gaussian process is a function which has a mean and a covariance. Okay. And if I just look at the thing on the left, the blue thing, the mean can define with this function m of x, and the covariance basically tells me the relationship between any 2 data points. And the covariance function is defined by a kernel function, which is called k. Okay. So if we now, so this is our prior, so we tend to specify a prior which has a 0 mean, and then without loss of generality, we can still fit any kind of different functions, even if we assume the prior mean is 0. And we then observe some data, and what we're doing is we're effectively trying to, how can I explain? So if I take you through what's in this equation, okay, so mu star is a prediction of the mean at a new point, okay, and sigma star squared is a prediction of the variance at a new point, okay. And what this is telling me is that the prediction of the mean depends on, so if you like, sigma n squared is a hyperparameter that we've fitted. K K relates to the data, and K star is a kind of compact notation which has some data and some hyperparameters buried inside it. So I guess what I'm trying to say is that both the mean and the variance can be predicted with these closed form solutions, which are essentially just functions of the existing data with a couple of things in there that we've fitted from the data. And I'll try and maybe I've got a better explanation somewhere here. Let's have a look. Yeah, maybe this is a bit clearer. So Y would be a vector of observed values. The big K here is the prior covariance matrix, which is positive semi-definite. Okay. So that's basically the covariance function applied to all of the existing data points. So from that, I get this matrix, big K. K star, so that's this small one here. That's the covariance between the existing data points and the new points that we want to make the computation at. Okay, so that's another matrix, which we calculate using the covariance function. So basically what I'm saying is we can make predictions of mu by saying matrix times by matrix plus matrix inverted times by vector minus whatever our assumption of the prime mean is, which is usually 0. And then a similar argument applies to the variance. I don't know if this helps, but it's just linear algebra. It looks complicated, but literally it's saying like, I'm going to get a vector by taking some matrices and a vector here. Does that make
Depends on
sense?
the data we have.
Yeah, exactly. And this is the key point with GPs. The data is the model, right? If we want to make predictions, we have to carry the existing data around and then do linear algebra with it to make predictions. And that's the good thing and the bad thing about GPs. It's a good thing because it's very transparent and very flexible. Like there isn't a model. The model is the data. But it's a bad thing because it's not scalable, because we have to invert the entire n by n matrix, big K.
I see. Okay, great. So yeah, so before we finish, I have a question for you, Dave, on behalf of our big data analytics subcommittee. So for students who will join the research in this field, specifically the battery state of health prediction diagnosis field, how can the students have access to some field data? Is there any, I saw you talk about the data availability, right? So is there any, where can they download, or do you have any suggestions for them to start?
Yeah, great question. So actually the data that's that we used in this work is all available openly. So if you go back here, so within this paper on the right hand side, which if you can't access this paper, just send me an email and I'll send you a copy. But all of the data in this paper is available. You can just download it. It's quite large, but you can still download it. Also, there's a very nice website called Battery Archive, which is run, I think it was from Sandia National Labs in the US, which has lots of battery data. So if you want to get some battery data, it's mostly lab data, not field data, but batteryarchive.org is a good place to go to look at some data and play around with it. And it's always being expanded, so I think it will grow over time as well. But I'd also say it is a general challenge. We need more data, and we need more data to be made openly available. Excuse me. A lot of companies have data, but they won't necessarily make it open.
Yes, that's privacy, right? For some manufacturers, they want to protect themselves.
Yeah, it's a big challenge.
Yes, I see. Okay.
Hey, Qiushi, can I ask you a very quick clarification questions? This is Ning with NC State.
Sure.
For the slide 34, you have this this comparison of different method. I just want to ask you, when you compare these benchmark method with the proposed method, did you actually use this stress factors with them as well, or they are just the original method without considering these stress factors?
No, so you're right. This is just the original method with the random walk parameters. So if you like, I guess the fairest comparison is probably between the blue curve and the green curve here, because the blue curve is without the stress factors. Yeah. Whereas
Okay, so the blue curve
the
and
orange
the blue
curve
are like an apple-to-apple type of comparison without the additional stress factors into the consideration. That means that the stress factors actually can improve the performance from here to here, right?
Yeah.
And then these
Yeah,
two,
definitely.
they're the same, right?
Yeah, I mean, I would argue that all of these are apples to apples, but I think for complete transparency, I mean, the benchmark is just there as a as a baseline comparison, but the benchmark really, if I didn't really talk about this slide. Let me just skip ahead one slide, but whoops, sorry. So you can see here on the left the difference that it makes to actually assume that the resistance is a function of temperature, voltage, current, and time, or to ignore that, right? So it just looks very, very noisy, and I think this noise is not caused by identifiability or observability problems or sensor issues. This is really caused by the fact that the thing is jumping around because it's a function of state of charge and current and temperature and so on, particularly current, right? If I look on the right hand side here, the variation resistance between like zero current and high current is like 1.58 ohms, which is massive, right? And that's going to completely swamp any changes over time. If you just look at this graph here, we can see that it's going along nice and smooth, and then towards the end of life it goes up from like, I don't know, half an ohm to like 3 ohms. So if it's like jumping around by 1.58 ohms just in normal usage, then we're going to get a very noisy kind of estimate. And that's really why the benchmark is not good as a failure predictor. And so maybe in some ways I'm being unfair, but I guess I just wanted to emphasize, that if we want to use resistance as an input for a battery failure predictor, we have to calibrate it. I guess that's the message here. But then the really interesting thing is that the stress factors do improve things a lot. Again, so I think what's going on here, and we've spent a lot of time thinking about this, but what's going on here is that the blue is really giving us some information about each specific battery. We've got 1,000 batteries, they're all a little bit different. The blue is telling us about each specific battery. The red is giving us a population average lifetime behavior. And if we put those two things together, then we get the orange, which is if you like, the best of both worlds, population average model and information about each specific trajectory, which is actually what's shown here on the left-hand side.
Yeah,
does that make sense?
That the reason I'm asking that question is that I was wondering if you use this model plus this one, will it give you a compatible
right
like that, right? Because that's
a great question.
Right?
Yeah, that's a great question. Yeah, I think we even did that. That's a great question. I can't remember what the result was, but I don't think it was as good as the orange, but I can't remember whether it was better than the red or not. maybe slightly better, but only at like the left-hand side.
Okay, yeah, thank you for the clarification.
That's okay.
Thank you very much. Very good presentation. Thank you.
Thanks.
Thank you, Professor Lu. So, all right, thank you, Professor Hovey, for your wonderful talk. Later on, we will create a personal web page for your video. We will upload your video after editing it. And yes, if you have any need, if you want to share your papers or data or whatever, please send them to us by email. We will put them on your personal website. So, okay, thank you again. And thanks. Very good presentation. I like it. Yeah.
Thanks for listening, everyone. Apologies, I covered a lot of different topics in a lot of detail. If anything was unclear or you want more information, just send me an email and, happy to talk further.
All right. Thank you. Bye-bye.
Bye.